Hello, Dr. April. Hello, everybody. For my math story today, I'm going to be talking about how Napier was the first person to discover logarithms and why he did it. So, firstly, for some background, in Napier's time, astronomers, navigators, and mathematicians had to do very large calculations by hand. And multiplying numbers and raising numbers to powers by hand took a very long time. And it was holding the astronomical fields, the mathematical fields back. And it was also making it very, very hard to navigate across the globe. So, as a result, Napier set out to create a method for multiplying numbers using addition. And I'm just going to go over it here. I'm going to go over how long it takes to multiply numbers as compared to adding them in this video here. So, I'm going to let myself take it away.
Hello everybody. So, as we all know, Napier lived in the 1500s. And back then, calculators didn't exist. So, all the calculations and stuff had to be done by hand. And while it's not all that bad for addition and subtraction, multiplication and division were pretty tedious. So, I'm just going to show why. Let's do some arithmetic. Some addition first. Now, as I said before, Napier was working with big numbers. So, let's get some big numbers. And this isn't going to be that bad. We all know how to add big numbers. 4 plus 3 is 7. 2 plus 8 is 10. Carry the 1. 9 plus 4. Well, 9 plus 4 is 13. 5 plus 6 is 11. 6 plus 5, 11. 8 plus 8, 16. 2 plus 3, 5. 1 plus 2, 3. And then we have all these numbers up here. We have 100. So we'll add 100 to that. We'll add 1,000, 10,000. We'll add 100,000 and a million. So we got a 4, a 2, a 2, 7, 6, 3. That wasn't very bad. That took like maybe a minute. Multiplication, different story. So I'm not even going to attempt to multiply 12 million by 23 million. I'm going to, let's say 924 plus or times 483. We truncated the numbers from before. This is going to take a long time because multiplication is distributive. We take the 4 times the 3, 2 times the 3, 9 times the 3, that's 1. Then we do the 4 times the 8, 2 times the 8, 9 times the 8, and we go to 400 as well. 400 times 4 times 20 times 900. Look at all these operations. And, for example, 4 times 3 is 12. So we have to add a 10 up here. And all these other numbers, these also have extra digits that we have to add up here. Add in this reserve up here. Like 8 times 2, that's a 16. We'd have to add 100 up there. And we have to do that for all the numbers. The reason for that is because, as we know, multiplication is distributive. 924 is the same as writing 900 plus 20 plus 4. And 483 is the same as writing 400 plus 8
80.
plus 3.
80.
This is the same thing. Even though it's a different order, normally we do first in, last out. 900, 400, 980, 903. We'd move on to 20, 20, 400, 20, 80, 20 times 3, and 4 times 400, 4 times 80, 4 times 3. And then we'd have a bunch of numbers down here. We'd have 900 times 400. 9 times 4 is 9, 18, 27, 36,000. We have the thousands. We'd have the hundreds. We'd have the tens, and we'd have the single digits. And we'd have to add the extra digits in reserve. And it's the same thing. Multiplication is distributive. So even though we did 900 times 3, if we reordered this, we could say 3 plus 80 plus 400
That's the commutative property, not the distributive property.
times 4 plus 20 plus 900. Up here, we did 3 times 4 first, 3 times 4, 3 times 20, 3 times 20, 3 times 900, 3 times 900. You get the picture. These are a lot of operations. More than one per column. If we counted it, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplication, which is super time consuming. So Napier wanted to find a way to do multiplication problems with just addition. And that's why I started experimenting, and that's how I found logarithms.
He found logarithms.
I'll explain that in a second.
I didn't find any logarithms. Napier did. I didn't discover anything. But it is time for logarithms. I'm going to be reading through, or at least describing, the first book that Napier described his logarithms in, the book that he had his logarithm tables in, Medifici Logarithmorum Kenosis Descriptio. And I'm going to be talking about that in the next video. So I'm going to take it away. Here I go.
Hello everybody, this is the next video, and I'm going to read Napier's documentation on how he figured this out and try to explain it geometrically to the best of my ability, because it's very vague and it's also in Latin. It comes from this book that Napier published after he discovered logarithms. It's 90 pages of logarithms, a bunch of other geometry, a bunch of words, a bunch of proofs, and its name is Medifici Logarithmium Canosis Descriptio. And this is, he just gave one blurb of text explaining how he came to the conclusion that you can have a logarithm table and multiply one side and get the result of that multiplication by adding the other side. Quote, and this is a translation from the Latin, one point moves at a constant speed along a line. Quote, another point moves along another line in a way that its distance decreases proportionally to its remaining distance from a fixed point. And this is how I interpreted that. So, there's one line of fixed length, and there's another line of infinite length. The first line and the second line are connected. There are two particles, and they both go the same speed along these lines, and each particle is an increment of time. So, let's say that this line is 1 unit long. We'll say a meter long. And we have a particle that goes half a meter per second. So this is a halfway mark, and the particle on line A travels 1/2 of a meter in that second. On line B, that same particle, or technically the particle in the second line, travels half a meter in that second. On line A, the distance of that particle decreases proportionally to its remaining distance from a fixed point. So how I interpreted it is, whatever percentage across this line it went, it goes that percentage again. So it went halfway this time, so it's going to go halfway across this line again. And this line B moves at a constant speed along the infinite line. So it goes half a meter again in that second. On the third second, it goes halfway again, and this goes half a meter. Halfway, half a meter. So I created a table based on this. Like Napier supposedly did. Where on one side, he has a number. He used Greek, so he called it the arithmos. And on the other side, he called it the logos arithmos, or logos, which means ratio, and arithmos, which means number, like right there. That arithmos means number. He concatenated the two words. He called it the logarithm. And over here, what I thought he had for the logarithm, which was actually incorrect. Over here, let's start with just particle 1, 0.5, 1, 1.5, 2, over here, he goes halfway, and then he adds another half, so half of that is an extra fourth, so he goes 0.5, then 0.75, then 0.75 plus an eighth, so 0.875, and then he goes a 16th, so 0.9375. I tried multiplying this side, and it doesn't correspond with the number over here, arithmos. And that's because I interpreted it incorrectly. What Napier actually measured was the distance to the end up here, and from here he measured the distance from the start. So actually, it goes 0.5, 0.25, aka a half, a quarter, 0.125, an eighth, 0.0625 for a 16th, I believe. Yes. And a 32nd. So 0.03125. And I don't know how he came to this conclusion, but Napier figured out that if you multiply, for example, 0.5 times 0.25, if you add the values of arithmos, the number, then at 1.5, you'll find the sum, or the product of that multiplication. And it works for every number on here. So let's say we want to multiply 0.5 times 0.125. Well, 0.5's number is 0.5, and 0.125's number is 1.5. So 0.5 plus 1.5 equals 2. 2 is 0.0625. So the result, the product of 0.5 times 0.125 should be 0.0625. And if we multiply 0.5 by 0.125, you'll notice that the result is correct. The product is correct. But there is something weird about Napier's logarithm table. It doesn't have any decimal points. And the reason why I realize is because even though it's decimal point accurate here, when you use a different ratio, like let's say, I'll pull it up. If your particles are going 10 meters per second and the length of the fixed line is 100 meters, well, it would end up looking like this. So our blue points are the points on line A, the red points are the points on line B. And I actually went through the effort to calculate it when I assumed that was the distance from the start and not from the end. I just found that I could still use this to graph this. However, with the actual equation, the actual values, at point 0 or at time 0, start at 100 meters from the end, and I'll go to 90 meters because it's going 10 meters per second. Over that distance, it travels a tenth, so it keeps multiplying it by a tenth. So, After that, it would be 81 meters from the end, then 72.9 meters from the end. And if you do math with these, let's say you want to multiply 90 and 72.9, the corresponding arithmos values are 1 and 3. 1 plus 3 is 4. At 4, the result is 65.61. The actual product of 90 and 72.9 is 6,561. Those are the same numbers, but they're not accurate to the decimal place.
All right. And what's the relationship between this table and modern logarithmic equations? Gonna discuss that in next video. Here we go.
Alright, for the third time, welcome back. And you might be wondering what this equation right here has to do with modern logarithmic
This equation.
equations. Because 100 quantity 1 minus 0.1 to the power of x is not a logarithmic equation. Actually, it's an exponential decay equation. Well, the answer is pretty simple. It's because, as we know, the modern logarithm's definition is the inverse of exponential equation. Base answer power and all that jazz. Well, the inverse is just when the output of a function is equal to the input of a separate function. And this is our table, our input and our output. For the logarithm, it's just swapped. Our input becomes our output, and our output becomes our input. Now, this isn't how Napier wrote it in his book, Medifici Logarithmoris Canasis Descriptio, but this is why it's named the logarithm, because this column is still called the logarithm, and this is called the arithmos. If you look at a modern example of a logarithm, you might notice it's reflected across this axis. Y equals x.
Y
To
equals
the power
x
of
is just a
x
straight line.
is our red equation, and log base 2 input x is our blue equation. You might notice our inputs and our outputs are swapped. 0 is corresponding to 1, and over here, 1 is corresponding to 0. 1 corresponds to 2, 2 corresponds to 1. 2 and 4, 4 and 2. 3 and 8, 8 and 3. 4 and 16, 16 and 4. 5 and 32, 32 and 5. The reason we call it the logarithm, instead of just making up some name for the inverse of an exponential equation, is because of the history behind it.
So why was this presentation so long? The reason that this video was so long was because I did put a lot of research into this presentation. I read a lot of sources and I watched a lot of videos, and I had a hard time condensing all that information into a simple 3 to 4 minute presentation. And I didn't do that. On top of that, I actually had even more content that I cut. So for example, I wanted to do an example where we created a logarithm table that was the inverse of an exponential, and to use that for multiplying, dividing, extracting roots, and exponentiating numbers. I also wanted to talk about, for example, why Euler's number is the base for the natural logarithm, and talk about the special derivative properties of e, and a few more things as well that I won't mention. But I just didn't have time to go into all of that. Um, so I apologize that this presentation was so long. And I also apologize that this presentation took so long to submit. But I just want to let you know that you were my favorite professor this semester. So, out of all my professors, out of all my classes, I liked your class the most. So, I want to thank you, no matter what, for teaching me this semester. Thank you, Dr. April, and goodbye.